Now let's prove the LGV lemma. So what do we need to prove? Well, I'm going to use the same notation from the previous lectures. S denotes a set of nodes. We have a weight function V from S cross S to the real numbers, and we have the usual notions of definitions of the weight of a path, and we have the non-crossing condition. I'm not going to write this down again. So what we need to prove in that setup is that the sum over all sigma in Sn, the sine of sigma times the sum over all n tuples of paths omega 1 omega n, where omega I goes from ai to b sigma I, product v omega I goes from 1 to n. So what I've written down here is just the determinant of the matrix M in the LGV lemma. So we need to show that this determinant is just the sum over omega 1 up to omega n, where omega I is from ai to bi, and these are pairwise non-crossing. Of product I goes from 1 to n v of omega I. So the sum on the right hand side is a sum of the sum on the left hand side, and what we are going to do is we are going to define a sign reversing involution which will cancel out all the terms on the left hand side except for the ones that survive on the right hand side. So to this end, let x denote the set of all n tuples of paths omega 1 omega n, where omega I is a path from ai to b sigma I for some permutation in Sn, and we'll also assume that the product I goes from 1 to n of the weight of omega I is not equal to 0 for each I. Otherwise, there's no contribution here to the left hand side. Now we'll define an involution on x. A sign reversing involution. So, I should define what the sign is. So the sign of omega 1 omega n is just defined to be the sign of the permutation sigma that underlies these omegas. Okay, now I'll define a sign reversing involution. So define I from x to x as follows. So firstly, if omega 1 to omega n contribute to the right hand side of this equation, we will define I to just be the identity map. So I of omega 1 omega n, so I to be so these will be fixed points, is equal to omega 1 omega n if omega I is from ai to bi and omega 1 through omega n are pairwise non-crossing. Now, otherwise, the definition of I is a little more complicated. So it's helpful here to draw a picture. So let's just take let I be the least. So firstly, if omega 1 and omega n are not non-crossing n-tuple, then there should be at least one crossing. So let I be the least integer such that omega I crosses omega j for some j greater than I. So you look for the first path that crosses another path. Now if omega I is the path S0 up to Sk, let m be the least integer, least index, such that omega I crosses some omega j at Sm. So Sm will be a common point of omega I and omega j. So you look for the first point on this path where it crosses another path. And then finally, let j be the least index such that omega I crosses omega j at the node Sm. And if omega j is the path T0 up to TL, let's say that Sm be Tr, the point of crossing, which we'll call P. So let's draw a picture. So we have A1, A2 and so on, and we have AI. We have a path omega I that starts out at AI. And say it ends up at B sigma I. Here we have B1, B2. Now this AI may cross several paths omega j. Now look for the first point where it crosses some other path. So this is the point what did I call it? I called it Sm. So this is the point Sm where it crosses another path omega j, which starts at Aj for j greater than I. And it may cross several paths here, but we look at the least j such that it crosses it. It may cross this path again, I don't know. And here we get B sigma j. Now what you do is you construct new paths omega prime I and omega prime j as follows. So we have omega, so remember we have omega I equals S0 up to Sm, Sm plus 1 up to Sk. And we have omega j to be T0 up to TL, no, TR and TR1, R plus 1 up to TL. Now define omega prime I to be the path S0 up to Sm, but after Sm, which is equal to TR, it goes to TR plus 1 up to TL. And define omega j prime to be T0 up to TR, and then after that it goes to Sm plus 1 up to Sl. sk. In this picture, what I'm doing is I'm taking the first half of this path and then combining it with the second half of the path omega j. So this is the path omega j. So this red path is omega prime I, and omega prime j is, the first part is the same as omega j, but the second part is the same as omega I. So this is omega prime j, the green path. And what we have is that the weight of omega, so now we'll define I of omega 1 omega n to be omega 1 up to, and then we'll replace omega I by omega I prime, we'll replace omega j by omega j prime, and we'll keep all the other paths same. What we have is that the weight of omega 1 up to omega n is equal to the weight of omega 1 I of omega 1 omega n. What I mean by the weight of an n tuple of paths is just the weight, the product of their weights. So the product of weights here is the same as the product of weights here, because totally the weights of omega prime I times omega prime j is the same product as the weights of omega I times omega j. Just look at the definition of the weight of a path is the product of the weights of the steps in the path. And since the totality of steps in the paths omega prime I and omega prime j are the same, this weight remains unchanged under the involution I. However, if we've defined the sign of omega 1 omega n to be the sign of sigma. Now what happens is that the permutation associated to I of omega 1 omega j is the permutation associated to omega 1 omega n with b sigma I and b sigma j interchanged. So what we have is sine of I omega 1 up to omega n is equal to minus sine of omega 1 up to omega n. So what we have is sum over omega 1 omega n in x of sine of omega 1 omega n times weight of omega 1 omega n. All the terms will cancel except for the ones where omega 1 to omega n are non-crossing. And because of the crossing condition, this will imply that omega I goes from ai to bi. And so what we have is that the left hand side of the LGV lemma is equal to all the terms cancel out except for the ones corresponding to pairwise non-crossing partitions. And so that concludes the proof of the LGV lemma. Now I want to make one observation about this proof. Where did we use the non-crossing condition? We used the non-crossing condition in just one place in this proof. We used it to conclude that we use the non-crossing condition to conclude that if omega 1, omega n are pairwise non-crossing, and omega I is from ai to b sigma I, then the crossing condition ensures that sigma is the identity, and the sign of the sigma, because the sign of the identity will be +1. So we can also formulate a slightly more general version of the LGV lemma without the crossing condition. I'll call it the generalized LGV lemma. Sometimes this is referred to as the LGV lemma. Without the crossing condition. So it says that given S, a set of nodes, V S cross S to R weight function such that and a matrix M equals Mij such that Mij, oh yeah, and we're also given A1, AN, B1, Bn in S, and a matrix Mij where M subscript Ij is the sum over all paths gamma from Ai to Bj of the weight of gamma. Then determinant of M is the sum over all omega configurations of paths omega 1 up to omega n which do not cross, and omega I is from some ai to b sigma I for some permutation sigma. But here we will still have the sign of sigma, and then the product I goes from 1 to n v of omega I. So now we have lost positivity, but we have we have a more general setting in which the LGV lemma applies.